Yes, thank you very much. Yeah, my name's David Pryce, and yeah, I work for Wandera. For those of you that don't know, that's a tech startup headquartered here in London that offers a software as a service to protect and monitor enterprise mobile devices. And I'll be telling you, as just mentioned, about malware and how we detect that on those mobile devices so that we can then protect them from all those bad guys. I have done this talk before at the San Francisco version of this conference, so I know that it won't exceed the 30 minutes, so you will be able to get to beer in good time. So, what I'm going to go through, firstly, just defining the problem and sort of why we have to worry about mobile phones and malware at all, which is obviously more the sort of marketing spiel of why we do the work we do. And then I'll go into more of the detail around the data and the machine learning that we then perform, and of course why we want to use something like Apache Spark. And then finally, I'll go into more detail about how we've made that a bit more production ready and are running it now in production. And of course, finally, we're hiring, the typical final slide. So firstly, the power of enterprise mobility. As we all know, there are various applications that you see on your phone and that you use all the time. And particularly now, we see more and more phones being used in an enterprise. So say you work for an end company, they're going to give you a nice spanking new iPhone, and it's going to have all these different communication tools on, like Slack, email, etc. That means you can then have a more flexible work-life balance, hopefully. You have access to more of the tools that you have both personally, so like Facebook, etc., but also these work-based applications. And as I just said, like email and other services are then available all the time, at any place in the world. But that, of course, opens us up to many more problems, many more threats, and many more issues. So, as I just mentioned, we're talking about malware, but there's things like phishing, cyber jacking, side-loading of apps, etc. So then there are other problems again. So the concerns around what you do with your phone and how you use it. We find many of the users that we see obviously going on pornographic sites. They're downloading from third-party app stores that maybe their admins don't want them to. A third is that data usage costs then go out of control. So downloading big files or looking at too many sites or things like this means that the costs that the users and the admins may or may not see just spiral out of control. And then the last, which is more of a general security issue, is exposing sensitive data. So all these communication channels are not necessarily as secure as you think, and that means you get leaks of passwords, credit card details, etc. And what this means is we now have a very happy hunting ground for attackers over various platforms. So malware is the one we're talking about here, but here's some big stats that we've seen in the last few years. So I'm not a big fan of the more than 100% stats, but 435% of high severity threats have grown in 2016. We've seen in our data that 80% of the organizations will experience a mobile phishing attack, and that's often the first step in an attack vector that could lead to a malicious app. 38% of hackers bypass endpoint defense using social engineering. So what does that mean? That means that they will send an email that then may contain a link or a spurious download, or even one of the most basic social engineering attacks I've ever seen, which isn't for mobile necessarily, is leaving like a USB or some sort of disk somewhere, and someone will be clever enough to plug that into their laptop, and then that will affect the network in some way. And you can do that in various platforms again. And a final stat there, that 100% of is the growth in which we've seen of mobile malware for 2016. And Gartner recently have said that mobile threats can no longer be ignored, such to the point where they've now made a new quadrant just for mobile threat defense itself. So, just to do a little spiel about what we actually offer. So this is our platform, which works on a secure mobile gateway. We have both on-device protection in an application. So that's where we're going to talk. That's where we're mostly going to talk about today, around monitoring applications that are downloaded and installed. But we also offer a traffic protection. That's looking at all the network traffic that comes off the device through the internet. More and more statistics. So this is just talking about how the rise in mobile malware. This is just for Android, but you can see every year on year, there are more and more mobile applications that are seen as malicious. This was just for 2017, but I believe for this year we're already exceeding the previous year's estimations of the number of malware samples out in the world. Of course, in the iOS world, it's a bit different. Many think that iOS is entirely secure due to their thinning and encryption that they perform on the App Store. But actually, in the last year or two, that has started to change, and we have started to see a rise. It's a lot less than Android, of course, that being an open source operating system. But iOS malware is definitely coming and on the rise. And then this slide here is just trying to drive home the fact that we're not just trying to detect malware, we're also trying to classify. There are many, many ways and types of malware that we can see. There we see ransomware, spyware, adware, and they have different severity levels. So our machine learning doesn't only detect, it also classifies. And I quite like this slide because it kind of lines up with my sort of scientific brain. I see things like chemistry and malware. It's quite a nice little metaphor. So that's the sort of basis for the problem. Like, there's lots of malware. We see many more mobile phones and much more data going through mobile phones than we ever saw before. But why is this novel? So, as I've mentioned, mobile malware is on the rise. But current detections, i.e. using signatures, so a lot of the time there'll be checks of like just hash or checksums. These were not really scalable as we have more and more data, and therefore aren't as effective. So we now need a solution that can work across both what we know, i.e. signatures, and what is then going to be an evolving space, so that we can then protect our customers, but also then enable more research into the ways in which these outbreaks will change. So as I say, the first solution was in signatures and lists, but our solution and many other solutions are in machine learning. So if I want to do machine learning, I have to have some data, some good data. And in this case, we wish to find both good apps and bad apps. That's our basic idea for supervised learning. We want to have labeled data of some really good, known good apps. So we look at official app stores in Google Play and the App Store. Stuff that we've actually seen in our estate on the devices. Again, we try and verify that with good research, good threat research. And of course, the final one, any traffic that we see that we might think is malicious, we try and attribute to a certain app, and therefore we have a version of a good or a bad app. So you combine all this data with threat intelligence, so we have a threat ops team, but we also go out and look into the community and see detections that have been detected but in the community to then verify our labels. And there we have the data, some good apps, bad apps, and labels of some form. Currently we have approximately 2 million labeled apps. That isn't that many if you think about how big the Google Play Store is or how big the App Store is, but it's a good representation of all the data that's out there. And then when we have that data, we then want to perform some sort of feature extraction. And this is where the things get a bit more difficult, a bit more complicated, because the things you can do with Android is different to the things you can do with iOS. So we're limited in the extraction that we can get out of iOS. So we focus primarily on the Android platform. And we try and get things like structured features in the sort of area and metadata of permissions and activities. So those are known like app metadatas that you can get very easily from just looking at a DEX file. Statistical features, so like the length of the code, the number of classes you might see in the code, the sort of types of classes used, the types of functions used. And the last one is just empirical features. So does the APK have a certain file in it or not? Does it have a certain type of executable in it or not? We then try and enumerate that as you would in any machine learning project to either get continuous or binary values. So then how we then extract them? So the reason this gets tricky is that every app may or may not have exactly the same set of features as another app. So for example, if we look at all of the data, the total unique fields approximately is around 500,000. But a typical app may only have 10 of those fields. And so what that means is you'll have a very sparse vector. You'll have a bunch of zeros everywhere, and those 10 ones will appear somewhere in that massive vector. And the solution to this is, one such solution, is to use a hashing function. That means that you can then perform a lookup of the features that you wish to very quickly, and hopefully if you pick a big enough hash map, you don't get any clashes. So that was the solution we chose to go for. Of course, there are many, many more. And next, we would then feed that data into some sort of machine learning. We actually tried a variety of models and algorithms. We then, in the end, selected logistic regression. Of course, to make sure that we pick the best parameters, we would do some sort of cross-validation. And in the end, we have an accuracy, we think, of around 0.96. That's very good, but that is also incredibly biased, thinking of the two classes we have. We have malware and not malware, and we have a lot more not malware. So accuracy is maybe not the best measure here, but if you look at other scores, it still does relatively well, and we've proved that in production, at least, that it still performs well enough. The main reason for choosing logistic regression was for speed of retraining and the fact that there were not many parameters that would need tuning, so we wouldn't have to run the cross-validation too many times till we had a model that we were happy with. So why would I even try and use Apache Spark? So I've already mentioned that we have around 2 million apps, and the feature space is around 500,000 features. In this case, we're using a hash map. That means that the data is truly big data, and it's always growing. Like, we're not really going to ignore something that we've seen in the past. We really want it to learn from something a long time ago, so that whenever we see that app again, it doesn't try and block it or delete it. So it truly is big data. Second, why use Apache Spark is its ease of use. There are many APIs. We predominantly use the Scala one, but of course, as you know, there's Java, Python, and ARM APIs. The deployment and scale. So it was very easy for us to go from development on a local machine to then looking at a cluster or in client mode. And finally, the fact that we could export our models into the PMML paradigm, which I'll go into more detail in a bit. So this is a very, very high-level diagram of how we would then go from this sort of local development to a production-ready model. Sadly, someone chose to use MongoDB at some point, so we had to. That's where our data was stored. If I was to change that, I would, definitely. We then, using the core Spark API, extract the features, like I mentioned, using that hashing function. Then using the MLib or ML, depending on which version of Spark you're using, API, we would then train up our logistic regression and perform the hyperparameter tuning. We would then, again using the ML API, trim the P.M.M.L and export that. So that's our saved model in a portable file type. And then finally, we'd push that to S3, again using the core Spark API, where it could then be picked up by our CI, which in this case is Jenkins or AWS Lambda, and push that into our REST API, in this case, OpenScoring. But what is PMML? So for those that don't know, you have probably heard people talk about PGA and PMML, and of course here at Spark and AI, there's much talk around ML flow, but this is another sort of framework for exporting machine learning models. So it stands for Predictive Model Markup Language. Before now, it's basically an industry standard that is monitored by the data mining group. The pros for it are that it's language agnostic, so if you have a Python sklearn model, you can export to PMML. There's a library for that. Like I just mentioned, there's one in Spark. I believe there is definitely one in R and some other languages as well. There are many REST APIs that will ingest said PMML and therefore expose an endpoint that you can score the model against. And there's a pretty good algorithmic coverage, which is something that we don't normally say with many of these third-party tools. The bad thing is that sometimes, and particularly for models like this, which has many features, has many data points, it creates a very large file size. And you can deploy via zipping the file up, but even so, that does restrict you in some way around deployment, especially when you try and wrap it in some sort of drop wizard process or something else like that. So that is not a great thing for that particular file type. So this slide is mostly around some of the things we had to go through, to the sort of problems that we came across when we did this model training and then PMML exporting. There was some mismatching between saving to PMML between the RDD land of MLib and the data frame land of ML. So we had to do a bit of porting between the two. One basically didn't support save to PMML, so we had to create our own code for doing that. And things like hacking a PMML itself to get out probabilities rather than pure predictions. Again, that's something that we had to create ourselves. And like I just mentioned, the size of the model was a big problem, so we had to do things like things that you wouldn't see normally in, say, TensorFlow, where you would trim floats to just make sure the file was just a little bit smaller. As I mentioned, zipping the file at the end and then deploying that way could be quicker. And finally, the overall time to train, it was actually, I did this today actually on a Spark cluster with around 7 executors. It takes around 2 hours. So the scalability of Spark really comes in handy, and that scales absolutely horizontally. If you just use two executors, it would take tens of hours. So as I just said, 7 does so in 2 hours. If you really wanted a model like in the next hour, you would just add a few more executors and it would work. So how does this work in production? So what we see here is just, again, a very high level. A user will install any new app. If it hasn't been seen before for that user, the REST API will be sent a request with all the features that it expects. So that's all the things like the activities, the permissions, etc. That then is scored against the most recent model. The response comes back, and if the score is greater than 0.9, so we definitely are sure that it's malware, we are notified, and the admins are notified about the installation. If it's serious enough, the admin can remove the app, or we can do that as well. So I think I've got even quicker than I thought, so I'll just spend a little time on this last slide. So yes, as I mentioned, I'm the lead data scientist at Wandera. We like to pride ourselves that we do innovative research under scalable architecture and with some efficient feature delivery, I won't lie. We do have many data scientists from around the world, including Stanford, Imperial, Cambridge and Oxford. We are based in the UK mostly, but we have offices in San Francisco and in the Czech Republic. And we aim to solve real-world problems that are predominantly around securing mobile devices. So we recently released a new feature to do phishing detection live and on the device. And currently, that's most of our aim is around like the security of these apps and devices. Thanks for listening, and if you have any questions, now's a good time. Otherwise, I'll be at the end.
Thank you.
Hi, thanks. Great talk.
Thank you.
You have 2 million data points and 500,000 features, which already sounds like you have to cut that down significantly, and you also have a heavily biased data set. Did you use any particular techniques to get around those challenges?
So one of the techniques that we tend to use is, in training at least, we've changed the distribution slightly. So we try and do as near to 50-50 as possible, but then whenever we test, we would try to do so with a natural distribution of the malware versus not. That way we don't waste too much time with the records we don't need, and the model can still separate those two populations.
Thank you.
Are you using any novice techniques for detecting phishing on mobile devices? I guess what are you doing differently than like normal phishing detectors, like checking some database, whether people have reported it? Are you using machine learning techniques?
Yes. So of course we initially started using Sophos or OpenFish or FishTank, which are known lists. But the problem with those is they block just on IP or domain, which is too high level. And secondly, there are way too many false positives. So if we were to put that into, and we did for a while, into a production environment, your users would be using their phone, and then suddenly they wouldn't be able to use, say, the Facebook app because you had blocked an IP that's suddenly been re-IP'd to Facebook. So that's not the cleverest way to do it. The way we do it, I shouldn't tell you too much because we just filed a patent, but is more based on the features you see in the exact request they send. So when they then access, say, not just facebook.com, but facebook.com/ all these other things, we check those things as well. And because of the form factor of mobile phones, i.e. there's a very small screen, you can't see the end of the request, that's how phishing attacks have now changed. And even more recently, we've started seeing, which is quite comical, puny code, which is just another encoding. But if you look at it, sometimes you get emojis later on in the thing where the phisher is basically just mocking everyone. And we're seeing more and more of this, like different form factors, different encodings that you just necessarily wouldn't get with a list.
Any questions?
By chance, did you, because you have 2 million of examples of like code, did you try to play a little bit with deep learning? Because if you have 2 million nice examples, you can put it to deep learning, learn what is this bad code.
The question is, did we use deep learning? Not for this particular model, and just because it's lots of data doesn't mean it's deep learningable. But we have an experimental version of our detection that basically transforms any of the code into an image, and then uses that image as a normal image detection would, and feeds that through a CNN. And tries to detect that way fairly efficiently. And there's actually, someone beat me to writing a paper about it, so you can go and search the internet for that paper, but it's actually quite an effective technique.
Okay, and you said that you have accuracy in 96%. What about recall?
Good question. Off the top of my head, I can't remember. We use F1, I think, or F0.5 normally, and I think on the last check that was around 0.8, which means it has a pretty good recall.
Okay, thank you.
Any other questions? Hold on, we want to catch.
I can hear him, but I think everyone else can.
Recording, so we want to catch the question.
So to follow up on that question, wow, that's loud. Do you know, is there a particular class of malware family that you're missing, or is there a particular type of benign application that the features you're generating is either misclassifying or is really good at classifying?
That's a good question. The way that we tend to fix that problem is by having a final class that's just called potentially unwanted. Mm-hmm. And so if we think that's often where we find things that we've missed. Mm-hmm. And we'll then, over some period of time, we'll then reanalyze that particular bucket of predictions. Okay. And then we can then potentially reclassify a new class. Mm-hmm. From memory, we do very well on ransomware and adware, but the others less so, just because there are less examples of them.
Okay, thanks.
Any others? Well, then you can go home, Ollie, and have a beer.
Thanks very much.
All right, thank you all for coming. A big hand to David, please.